The Earth, where we live today, was formed by dust and gas about 4.5 billion years ago. The Earth was extremely hot when it first formed, and the surface of Earth started to cool down as time flows. However, the core of Earth still releases heat. The Earth's internal heat comes from primordial heat and radioactive decay. Half of the Earth's internal heat is left over from when our planet was formed about 4.5 billion years ago, which is called primordial heat. And radioactive decay is a process where some elements are unstable because the center of the atom, called the nucleus, is too big and will fall apart over time. In the process of falling apart, it releases energy, which can take around 0.0015 seconds to 4.5 billion years to occur, depending on the decaying substance. In the very early stages of the Earth's history, internal temperature and heat flows were probably much higher than they are today, partly because the planet had only just started to cool, and partly because of energy flow from radioactive decay was much larger. And the main heat transfer mechanism that takes internal heat from deep in Earth's mantle to near surface region is convection. The structure of the Earth is mainly categorized in four parts: crust, mantle, outer core, and inner core. The lithosphere and the asthenosphere are also included. While the crust and the lithosphere, which include the crust and the most top part of the mantle, and the inner core of Earth is solid. The asthenosphere, which includes the upper mantle, outer core, and deeper part of the mantle, is more fluid than other solid part, so convection currents occur in this fluid part. The convection in mantle is caused by the higher temperature in the inner core. When the particles at the bottom of the mantle is heated up, the mantle rises up because of the particles move faster and move further from each other, causing the mantle to have lower density. When it reaches the top, it pushes the particles to the side, and the pushed particles will drop down as it cools down because of the density increases as the particle slows down. When it drops down, it pushes the particle at the side of the bottom to the middle, and it will get heats up again, rises up, pushed, and repeat the cycle. As these convection currents occur in Earth will also cause divergent boundaries. When the convection currents appears in the asthenosphere while the temperature of the asthenosphere is hot enough to allow the asthenosphere drive the plates to move in a plastic-like form, then the top of the asthenosphere, or the lithosphere, will slide over the top of the asthenosphere and make a divergent plate boundaries. There are a few real-world examples for this. The Mid-Atlantic Ridge is an example of divergent plate boundaries, which was created by plate drifting apart. And as the lava cools down, the rocks form and spread from the Mid-Atlantic Ridge. The Red Sea Rift is also another example of the divergent boundary. The Red Sea Rift was created by the spreading of the plates, the African plate and the Arabian plate. And if two plates continue spreading out, the ocean will flow through the rifted valley, and the plate will completely become two parts. However, it will take a huge amount of time since plates are only spread out for a few centimeters per year. While the convergent boundary occurs when two plates move closer and closer, then one of the plates, which is denser, will sink under the other plate, which is known as subduction. The convergent boundary can occur between two continental boundaries, one oceanic and one continental boundary, or two oceanic boundaries. Between two continental plates, the more dense plate will sink to the bottom of the other lesser dense plate. Between the continental and oceanic plate, the oceanic plate will always be more dense than the continental plate, so the oceanic plate will sink to the bottom of the continental plate, and while this happens, the oceanic plate that sinks to the bottom of the continental plate will decrease the melting point of the rocks under, so that volcanoes will form. Between two oceanic plates, the more dense plate will sink, and as same as the continental oceanic boundary, the melting point of the rocks will be decreased, as the oceanic plates sink to the bottom of the continental plate. There are few real-world examples for the convergent boundary. The example of continental-continental convergent boundaries are the collision of Indian plates with the Eurasian plate, creating the Himalayas mountains, and the examples of oceanic convergent zones are subduction of the Pacific plate south of Alaska, creating the Aleutian Islands, and under the Philippine plate, where it creates the Marianas Trench, the deepest part of the ocean. Why the convergent boundary and divergent boundary happen in the same time? While the convergent boundary appears, divergent boundary will also appear somewhere on the Earth. If the divergent boundary occurs, then new land will be created, and the ordinary plates will move further and further, which means that the area of land will increase. However, to make balance of the Earth, the convergent boundary will also appear at the same time when divergent boundary occurs. So when the convergent boundary appears, then one of the plates, which is denser plate, will sink under the other plate. Therefore, while land are created, some land will be destroyed so that Earth can be balanced. As the convergent boundaries and the divergent boundaries appear on the Earth, it will lead to earthquakes since plates move, and the earthquake makes seismic waves. There are two major types of seismic waves, which are S wave and P wave. S wave is a type of seismic wave that moves the ground up and down or side to side, and P wave is a type of seismic wave that compresses and expands the ground. In the solid part of the Earth's interior, the particles are close together, such as the crust and the inner core. So both S waves and P waves can easily travel through the layers. However, the P wave can travel through liquids, and the S waves cannot. This happens because of the movement of the particles. In liquids, P wave can travel through it because particles bump into each other to move forward and backward, but it will be slower because some of the particles might not bump into each other in the right direction. S waves, or the waves that attract other particles to move up and down together, will not travel through liquid, since the particles are not very close to each other, so the force between the particles is weaker than it is in solid rocks, which means they cannot attract other particles to move under the same momentum, so the waves can no longer travel through the liquids. Because of the properties of how S wave travels, we can estimate the size and the location of outer core by the size of S wave shadow zone. S wave stops when it touches liquid, so when S wave stops, we know that it touches the outer core. Therefore, the bigger the S wave shadow zone is, the bigger the core will be. On the other hand, P wave shadow zone can indicate the location of outer core and inner core, since it slows down instead of disappearing when it touches liquid. Because of that, P wave travels through outer core and inner core, and from the refraction when they transfer from outer core to inner core, we can tell the location of the inner core. Seafloor spreading is also a result of divergent plate boundary, which is caused by convection, since divergent boundaries is formed by plate moving apart. The magnetic field striping will also support the theory of seafloor spreading. Rocks are formed by magmas cooling down, and when they are still liquid, their polarity follows the magnetic field of the Earth. But after it cools down, the polarity in the rock is stuck, and in the process of rocks being formed, the previously formed rock are being pushed out simultaneously. If the Earth's magnetic field change, the rock polarity changes as well, which causes the magnetic striping at the bottom of the ocean. And because of the magnetic stripe of the different age of the rocks are different, it shows the spreading of the seafloor.